Hello friends. So, we have seen the power iterations in action for computing the how any arbitrary vector can be nudged towards the eigenvector corresponding to dominant eigenvalue, and we explained that this is why the search directions for higher powers of matrix A in Krylov subspace, they tend to lose their independence, and they need to be re-orthogonalized or made independent of each other by virtue of by using the Gram-Schmidt orthogonalization process. So, before discussing some of the algorithms for solution of this algebraic eigenvalue problem, let us first go through the basic tools of the trade, the basic workhorse that are used in this solution of this eigenvalue problem, algebraic eigenvalue problem. So, first of all, let us ascertain, I mean since we are working with digital computers, and we all know what are the problems with floating point operation, and everything is approximate. So, what is the sensitivity of the eigenvalue, computing computed eigenvalue to the approximation? I mean computed approximation, because the matrix A that we are targeting, for which we are trying to compute the eigenvalues and eigenvector, that matrix A itself may be approximate. That may not be exact representation of the matrix A that is actually that should actually be representative of the system, because of floating point arithmetic and round off errors. So, matrix A can still be can itself be in error. So, the natural question arises, do small errors in matrix A, it can be a good approximation, but it is a approximation nonetheless with some errors. So, do small errors in matrix A imply small errors in the computed eigenvalue? Under what conditions? If it is true, if small errors in matrix A are they imply small errors, I mean the errors in the computed eigenvalues are also small, then obviously the computation is robust. Otherwise, we may need to take precaution. So, under what conditions does this happen? So, let us derive this result. Let us consider that delta A is the error matrix. So, instead of A, it is A plus delta A, which is the true matrix representing the system. So, that will change the eigenvalue problem from A x is equal to lambda x to A plus delta A multiplied by x plus delta x. So, delta x is the incremental change in the eigenvector, because for small changes in matrix A, we do not expect very large changes in the eigenvalue solution. So, this is a small change in matrix A in the neighborhood. So, eigenvectors will also be in the neighborhood and eigenvalues will also be in the neighborhood. So, x plus delta x. So, A plus delta A multiplied by x plus delta x is equal to lambda plus delta lambda. So, small increment in eigenvalue multiplied by the incremental eigenvector. Now, let us work out this expansion, and this results into this change in eigenvalue. So, lambda x, because this is what we are interested in, small errors in the computed eigenvalues. So, what is the change in eigenvalue? So, delta lambda times x is equal to A times delta x plus delta A times x minus lambda times delta x, and we are ignoring the higher order terms. So, product of small terms, for example, product of delta A with delta x is ignored, and product of delta lambda with delta x is ignored. And by invoking the orthogonality, we pre-multiply by the left eigenvector. So, we have delta lambda is equal to y transpose x. So, this will be scalar and that is what we take it in the denominator here. So, for the left eigenvector for the same eigenvalue. So, not orthogonality. So, of the same eigenvalue. So, we multiply this by y transpose A delta A x and this is scaled by y transpose x, that is the scalar. And we take the norms, what happens is if we take these norms, then delta lambda will be equal to, I mean now we can look at the individual terms. So, these norms will be equal to product of individual norms, that will be less than individual norms. So, delta lambda, the magnitude of the error in eigenvalue lambda will be less than the norm of y 2 multiplied by norm of x 2 x, that is the second norm. So, Euclidean norm divided by the norm, I mean the whatever is the magnitude of this scalar y transpose x, and then this second norm of this matrix delta A. So, this will be the spectral norm. So, largest eigenvalue of delta A. So, sensitivity of eigenvalue S, this is referred to this sensitivity of the eigenvalue. So, this is what scales the error, this is the measure of error in matrix A. So, this error in matrix A is scaled by this constant and this is called the sensitivity. If this sensitivity is small, then the error in the corresponding eigenvalue is also going to be small. And this depends on, of course, this is of course if we scale, then scale to unity, then this will be of unit length, y and x they can be scaled to unity. So, they will be of unit length. So, this scaling sensitivity factor depends on this denominator y transpose x. So, what is this y transpose x? This is the projection of y along x. So, this is the cosine of the angle between these two vectors, and value of the cosine function varies between +1 to -1, and it will be +1 or -1 only when the angle between the two vectors is 0 or 180 degree. So, the only way this becomes equal to 1, that is when the sensitivity of the eigenvalues would not be, I mean the error in eigenvalues will not be amplified by a factor greater than 1 with respect to the error in the matrix A. So, that is when y and x, if they are identical, that is when the left eigenvectors and right eigenvectors are identical. So, if they are identical, then that angle is going to be 0, angle between them is going to be 0, and this product y transpose x is going to be equal to unity, because these are the cosine between the two vectors is going to be unity. And therefore, we can conclude that for symmetric matrices, the left and right eigenvectors are identical and the sensitivity of the eigenvalues to errors in A is small. And that is why it is important, I mean in the beginning we emphasized that generalized eigenvalue problem can be converted to standard eigenvalue problem, but the trivial procedure of computing B inverse A and writing that as a standard eigenvalue problem is not a preferred technique, preferred way. Because of this reason, it will increase the sensitivity of the computed eigenvalues to the errors in the matrix of I mean the operator matrix, the B inverse A, because B inverse A is not going to be symmetric, is not guaranteed to be symmetric, and left eigenvectors will be in general different from the right eigenvectors, and then the sensitivity will be greater than 1. So, that is the basis for doing all that jugglery to convert generalized eigenvalue problem into standard eigenvalue problem instead of going through the straight route of B inverse A. So, this we discussed only to emphasize the need for that Cholesky decomposition of matrix B and always maintaining the symmetry of the matrix if the original matrices are symmetric to begin with. That is a very valuable property and we should not lose that in computation. So, symmetry is always a symmetry of the operator matrices is always a desirable property for any numerical computation. Now, we come to one of the very powerful tools of eigenvalue computation, that is called similarity transform. So, similarity transform refers to a transformation of the system matrices in such a way that although the matrix may change, but its eigenvalues are not changed. So, the basic idea is if we have two matrices, two square matrices A and B, then there exists a positive definite matrix C such that AC is equal to CB. That can be proven. And if C is positive definite, then obviously I can write C inverse AC is equal to B. And if I can do that, so if lambda and x, they are the eigenvalues and eigenvectors of matrix B, then I can write this as ACX is equal to CBX by post multiplying with x, and CBX is equal to lambda x. So, Bx is equal to lambda x. So, that will be lambda Cx. So, that is lambda is also an eigenvalue of A with Cx. I mean, if I can look at this as a vector Cx, C times x is a vector, then this is simply the eigenvector of A, and lambda is also the eigenvalue of matrix A. So, that means I can take C from right hand side to left hand side. So, C inverse A C x is equal to lambda x. So, that means that eigenvalues of A are preserved under the transformation C inverse A C for any positive definite C, right. So, lambda is the eigenvalue of A, and if I can find some matrix C inverse A C where C is a positive definite matrix, then this C inverse A C also possesses the same eigenvalue lambda, and that is a very powerful result, because I can nudge matrix A to a form by using this similarity transform to a form which allows for easier computation of the eigenvalues and eigenvectors. I mean, we can find the whole point is finding the determinant. I mean, by definition it is the determinant should vanish, and the easiest way to find the determinant is the simplest structure, simplest matrix for which determinant is easiest to compute is the diagonal matrix. So, if I can somehow arrange the sequence of operations such that C inverse A C gradually changes to a diagonal structure, then the problem is solved. We have computed all the eigenvalues of the system, and this basic idea forms the basis of several eigenvalue computation algorithms. But as I said earlier, I have been emphasizing on this aspect repeatedly. C inverse, I mean this inverse of matrix C should never be computed. I mean we should never be asked to compute inverse of a matrix, that is too much of an effort and too error prone, because it requires lots of floating point arithmetic operations, and each floating point arithmetic operation incurs a round of error. So, this C inverse computation should be avoided. So, the solution is of course, if I choose C as an orthonormal matrix, orthogonal matrix, right. So, if I choose C as an orthonormal matrix, then the inverse of C is computed, is given by the transpose of C. So, C transpose becomes its inverse. So, I can define similarity transform by using a transpose of a matrix, orthonormal matrix. So, I have to choose the matrix C in such a way that it is comprising of orthonormal representation. And because the eigenvalues of these two matrices are similar, are identical, these two matrices A and C inverse AC, they are said to be similar. And if C is orthonormal, then C inverse is identical with C transpose, and C transpose AC is called, this operation is called orthogonal similarity transform. So, if C matrix is an orthonormal matrix, then C transpose AC is referred to as orthogonal similarity transform, and that forms the backbone of most of the algorithms for solving eigenvalue problem, as we will see. So, the first example of this orthogonal transformation is what we refer to as Given's rotation. Now, this Given's rotation is similar to what we have in the coordinate transformation for reorientation of frame element local coordinate system to global coordinate system. We will see that. So, something similar to rotation matrix, that is orthogonal matrix. So, coefficient matrix A is progressively nudged towards a diagonal form by successive orthogonal similarity transform, and the idea, the goal is to make an off diagonal element vanish at one time. So, what happens is we define, I mean we have some elements, let us say x1 is on some diagonal and x2 is an off diagonal element in the same column. So, let us just look at these two elements, and it is pre-multiplied by this operation. So, cos theta minus sin theta cos theta. So, this is what if you recall, this is what we had for transformation of coordinate system from local coordinate to global coordinate in truss problems or even for frame problems. So, we try to map this, as our objective is to make this off diagonal term x2 to vanish. So, that this is the result. So, we want this term to vanish, and if we want this term to vanish, that is possible when I look at this second line of equation, x1 sin theta plus x2 cos theta should be equal to 0, and that gives me the result. By knowing these x1 and x2, I find out what should be the values of cos theta and what should be the value of sin theta, which will give me this result, right. So, if it is x1 sin theta plus x2 cos theta is equal to 0, then the simpler arrangement is I just make x1 or sin theta to be proportional to minus x2 and cos theta to be proportional to x1, and then it should be done, and that is what is done here. Problem is solved by using cos theta, defining cos theta as x1 divided by square root of x1 squared plus x2 squared, and sin theta as negative of x 2 divided by square root of x 1 squared and x 2 squared. With this choice of sin theta and cos theta, if we evaluate, then this problem will be solved. So, the off diagonal term x 2 is the off diagonal term, and that will be solved, that will be annihilated, and that is the objective. Gradually we need to nudge the matrix to a diagonal form. So, if we call this as a, so this forms the basis of Given's rotation. So, Given's rotation is essentially an modification of an identity matrix with these 4 terms cos theta minus sin theta and sin theta and cos theta, they only modify the 4 places of the identity matrix. So, II, ij, ji and jj, and this is to annihilate the element ij of matrix A, right. So, rest of the identity matrix remains same. We only look at II, ij, ji and jj, and these coefficient actually go as II element goes as cos theta, ijth element goes as minus sin theta, ji goes as sin theta and jj goes as cos theta. So, gii cos theta, gij minus sin theta, gji sin theta, gjj cos theta. So, that G transpose A would have a 0 in ijth position. So, if we multiply this, then ijth position would be vanished. So, these trigonometric functions, they are terms are evaluated based on the same evaluation that we had in terms of x 1 x 2. Instead of x 1 x 2, we now have aii and aij corresponding elements of the matrix, and these cos theta and sin theta are evaluated, and the cosine the Given's rotation matrix is defined. Now, to complete the similarity transform, we have to post multiply it with G. That would be the complete similarity transform. So, after that would be orthogonal similarity transform, that is affected by the product G transpose A G. Now, G transpose A has annihilated ijth position to be 0, that has forced ijth position to be 0. This post multiplication by G may again make it non-zero, but that magnitude wise it will be smaller than the original value. So, post multiplication by G generally makes ijth element non-zero, but it is of a smaller magnitude than before. So, what we are doing is we are shifting the mass of the matrix towards the diagonal. So, that gradually the entire mass of the matrix would be accumulated towards on the diagonal of the matrix, and those diagonal elements would be the eigenvalues of the matrix, given matrix A. So, this is Given's rotation, which actually targets one element at a time to make it vanish. Another powerful technique is called householder transformation. In contrast with the Given's rotation, where we target only one element at a time, householder transformation actually targets one whole column at a time. So, it makes one whole column to vanish in one similarity transform. So, it is possible to define a reflection of a vector about a plane through the origin, such that resulting vector is a multiple of the first Euclidean unit vector E 1. So, E 1 is 1 0 0 0 0. So, that is the starting vector we start with. So, householder reflection matrix is defined as P 1 as I minus 2 over V transpose V multiplied by V V transpose, such that P 1 when multiplied by x, it will make it proportional to E 1. So, that except for the first element, all the elements of this vector would vanish. very powerful technique. So, instead of Given's rotation which looks at which operates element by element, one element at a time, Householder matrix would make all elements but one to vanish, and the way to do that is by suitable choice of this vector. I mean, this vector v can be chosen such that x, it can be plus or minus using this scalar multiple, I mean the norm of length of vector x multiplied by the Euclidean first Euclidean unit vector E1. So, sign of this term is chosen to be same as that of the first element to avoid catastrophic cancellation during the subtraction operation. So, if it is of the same sign as the original vector, then there is no chance of incurring any errors due to this catastrophic cancellation. So, this is essentially the Householder matrix. So, this is the plane, and this P matrix is causes the reflection of this matrix along about this plane onto the first Euclidean vector. And Householder matrix P is symmetric and orthonormal, and this is a workhorse. We can keep on multiplying this repeatedly. So, first column we will make it vanish all the elements except the first. Second matrix P2, it will make vanish all the elements except the second diagonal, and so on. So, this way we can actually make the convert the square matrix to upper triangular form very easily in a very quick manner, and they are also orthogonal matrices. So, they are implemented, they can be implemented as rank 1 updates. So, this is actually rank 1 update. So, P A is implemented as A minus V W transpose, and W, I mean these are all numerical implementation issues for efficient computation, and this matrix P, the transformation matrix, is completely defined once we define this vector x and vector v, and which is defined, which is completely defined by the vector x which is to be reflected. So, finally, I mean at the beginning of the discussion of iterative schemes, we said that we can identify what is the largest eigenvalue of a matrix A just by inspection, and that is defined by Gershgorin-Redai. So, we can impose bounds on the eigenvalues. So, we can find the range between which at least one eigenvalue of the matrix will lie, and once I have this range by using this Gershgorin radius, there will be as many radius, as many disks as the number of rows in the matrix. So, for an n by n matrix, there will be n number of disks. So, I can get the largest disk, and I can get the estimate of the or bounds on the eigenvalues, that eigenvalue will lie between these, and I can choose the largest bound, upper bound, and that can be used for construction of the matrix G that we defined for construction of iteration scheme for Jacobi and Gauss-Seidel iteration, and that will ensure convergence of the matrix. So, we wanted that matrix to be matrix B to be B inverse to be equal to 2 by mu times identity matrix, and mu is the estimate of largest eigenvalue, and that largest eigenvalue estimate can be obtained from this Gershgorin-Redai, and that is equal to simply the diagonal element of the matrix A of each row, and multiplied added to the of sum of all diagonal elements. So, basically the idea is eigenvalue is bounded by the diagonal element of any row minus the sum of off diagonal elements, absolute value of sum of all the off diagonal elements, and the diagonal element plus sum of all off diagonal elements, absolute value. So, these are the bounds that are on the available on the eigenvalues, and the larger of these can be computed, can be worked out as the estimate for choosing the matrix for iteration, and that will complete our discussion. That will facilitate convergence of the iterative scheme. So, we stop here, and next lecture we will discuss about specific techniques of eigenvalue computation by using these tricks, I mean basic tools of computation, similarity transform, Gibbons rotation, Householder transform, and also Gershgorin-Redai. So, that provides us initial estimate of the eigenvalue, and using these we will compute, we will discuss some of the very powerful numerical algorithms for solution of eigenvalue problems. Thank you.